Take a look at this. It's a crystal, a solid, perfectly ordered structure. But what if I told you we could melt it with nothing but a magnetic field? Seriously, no heat, just magnetism. It sounds like something out of science fiction, right? Well, it's a real experiment, and we're about to break down exactly how it works.
Think about it for a second. Melting 101. You add energy, right? Usually heat. You crank up the temperature to break the bonds holding a solid together. But what if there was another way? A totally different way? What if you could turn a solid into a liquid just by, flipping on a magnet? That is the wild puzzle we're digging into today.
And here's the proof. On the left, you've got thousands of tiny particles locked into this perfect, solid crystal. And on the right, after hitting it with a magnetic field, that beautiful order is just gone. It's turned into this disordered, liquid-like soup. And remember, not a single degree of heat was added. So what on earth is actually happening here?
Okay, to solve this mystery, we've got to get to know our main character. This isn't just any old crystal you'd find in a cave. No, this is a plasma crystal, and it's a truly bizarre form of matter.
It all starts with something called a dusty plasma. So we all know the basics, right? Solid, liquid, gas, and plasma. Well, a dusty plasma is a special kind of plasma with one extra ingredient thrown into the mix. Tiny, solid microparticles, basically dust. These little dust particles get blasted by electrons from the plasma, which gives them a massive negative charge. And that charge, right there, that's the key to this whole thing.
Because all those dust particles are so intensely negative, they repel each other like crazy. And if you get the conditions just right, those repulsive forces push all the particles apart until they find this perfect, stable, balanced arrangement, and they literally lock into place. They form this stunningly perfect crystal lattice. It's a solid, but it's not held together by chemical bonds. It's held together by pure electrostatic repulsion, and that makes it very, very fragile.
So where did this all go down? Let's take a look at the crime scene, the experimental setup where scientists figured all this out.
Welcome to the Magnetized Dusty Plasma Experiment, or MDPX, at Auburn University. That glowing disk you see right in the middle? That's our plasma crystal, just levitating there between two electrodes. The entire machine is built around a massive superconducting magnet, and that magnet, well, that's our culprit.
All right, so the stage is set. We have our delicate little crystal. Now, let's see what happens when the scientists start cranking up that magnetic field.
The very first thing they noticed was odd. As soon as they turned on the magnet, the entire crystal, the whole solid thing, began to spin. Not violently, just a slow, kind of majestic rotation.
Here's our first piece of evidence. At about half a Tesla, and just so you know, that's a very powerful magnetic field, you can see from the velocity vectors that the whole crystal is rotating as one solid piece. It's this clean, uniform spin, almost like a record on a turntable. But watch what happens as they turn up the juice.
As they increase the field, the rotation gets faster. You can see the colors shifting, the little velocity arrows are getting longer, especially out toward the edges. This is our first clue that something isn't quite right. The rotation isn't perfectly uniform anymore.
And now, at a full Tesla, the effect is just dramatic. The edges are clearly spinning way faster than the center. This is the critical clue we've been looking for. The crystal isn't behaving like a solid object anymore. It's literally starting to tear itself apart.
So this is the crucial point. The crystal isn't spinning like a solid frisbee. The outer rim is going faster than the inner core. This difference in speed creates this internal stress, a force called shear. Think of an ice skater spinning. Now imagine her torso tried to spin at a different speed than her arms. Ouch, right? Something would have to give. That's the exact kind of force we're dealing with here.
This rotational shear is our prime suspect. So now, let's look at the evidence, frame by frame, and watch exactly how this force tore our perfect crystal to shreds.
So here's our baseline. Before any magnets, on the left the raw image of the particles, and on the right you see a map where every particle gets its own little cell. And notice, they're almost all perfect hexagons. That beautiful pattern, that's the fingerprint of a solid crystalline state. Perfect, long-range order.
Okay, magnet on. We're at that intermediate state. The rotation and the shear have started. And just look at the structure now. Those perfect hexagons, they're getting warped. We're starting to see cells with 5 or 7 sides popping up all over the place. The order is starting to break. The crystal is under stress, and you can see it.
And here it is, the final state at 1 Tesla. The smoking gun. That hexagonal structure is almost completely gone. It's just a chaotic jumble of different shapes and sizes. The shear force has completely broken the bonds holding the crystal together. This is not a solid anymore. For all intents and purposes, it is melted.
So, we've seen what happened. Now let's put all the pieces together and officially close the case on how a magnetic field can in fact melt a crystal. So here's the whole chain of events. First, the magnetic field gets things spinning. But, and this is the key, that rotation isn't uniform. That creates an internal stress, the shear force. That force just builds and builds until it's stronger than the electrostatic bonds holding the crystal together. The bonds snap, the structure collapses, and the solid melts into a liquid. Simple as that.
And hey, don't just take my word for it. The scientists who ran this whole experiment came to a very clear conclusion. They said that the induced rotation is the dominant mechanism that leads to the crystal melting. Case closed. In the end, it was the spin that shattered the solid. Now, this is way more than just a cool physics trick. This shows us a fundamentally new way to control the state of matter. We're not just dumping random heat energy in, we're using precise, directed mechanical forces generated by a magnetic field to trigger a phase transition. And that leaves us with a really fascinating question. If we can melt a solid with magnetism, what else can we control?